Hello and welcome to the ARC Automation Studio. I'm Alan Avery, a Senior Analyst here at ARC Advisory Group, and today's topic is microgrids. And joining us is Rick Riss, a Senior Consultant here at ARC, and he's just completed a research project on this topic. Thanks for joining us today, Rick. I wonder if we could start off by going over your background and how it relates to microgrids.
For my background, I have degrees in chemical and electrical engineering. My first job out of college was as a process engineer at an electrolytic chlorine plant in Niagara Falls, where I worked for 3 years. I then moved back to Massachusetts and worked as a control system engineer for 20 years at the Foxborough Company, now part of Schneider Electric. I worked designing, building, and starting up control systems in refining, chemicals, electric power, and actually a number of other industries. My specialties have been in distillation, compressor, and reactor control systems. In 1996, I formed my own independent consulting company, R2 Controls. Having left Foxborough Company on good terms, I continued to work as a contractor ever since, and worked on many projects, including the China nuclear project, producing control and safety systems for 8 nuclear power plants that are recently in full operating production. I've been working for the past 4 years as a consulting analyst for ARC, creating market studies in the areas of operator training simulators, HVAC control systems, substation automation, transmission and distribution SCADA systems, grid-scale batteries, and microgrids. Working with a team, I designed and built my own net zero house to German passive house standards with a solar PV system, an off-grid inverter, and EV charging infrastructure. I'm also a light commissioner in our small rural town that manages a distribution system for about 1,200 households. Our town owns and operates 2 1.5 megawatt wind turbines operational since 2009. So over my career, I have moved my focus from process control to electric grid control.
Thanks, Rick. I'm wondering, just what is a microgrid and what are some of its attributes? How does it fit into the overall larger power infrastructure?
What is a microgrid? Sounds like a simple question, but not everybody gives it the same answer. The term microgrid is not defined the same way by everyone. In this simplified line drawing, a hypothetical microgrid is shown on the right side with a single point of connection to a larger main grid on the left. Microgrids tend to be more common on the distribution side of a network. They typically involve renewable generation, but not always. They are typically under 30,000 volts. With residential grids referred to as nanogrids and very large grids called mini-grids, the exact size boundary for microgrids tends to be a bit arbitrary. For ARC, we limit a microgrid as any grid between 20 kilowatts and 100 megawatts that can operate in island or off-grid mode. So 20 kilowatts would be a bit large for a residential system, probably be a small commercial system. 100 megawatts is a pretty large grid, might be the size of a university campus that has significant generation assets as part of their electric grid. Regarding what is a microgrid, some people define microgrids as including generation assets like diesel generators, wind and solar. ARC focuses on the automation part of microgrids, so we exclude generation assets like fossil power generators, wind and solar generation, and load assets like thermal storage and HVAC related equipment. Where microgrids interact with these devices, we do include all the automation hardware, software, and related services. So far in the microgrid study, we have included grid-scale batteries as part of the microgrid automation, but we do provide market data that excludes the battery content. There are a handful of microgrid suppliers for automation that can provide a battery in a box, which is essentially a microgrid by itself, ready to go, plug and play. we will include building management, energy management, HVAC controls if they are provided as part of the microgrid. In the segmentation of microgrids, ARC defines 3 levels of control. The primary level is associated with safety, protection, switchgear. This level would include items like circuit breakers, reclosers, protective related measurements like current voltage, frequency, may include synchrophasers, if they are provided separately from the circuit breakers and recloser functions. At the secondary level, this is really the local management and control of the distributed energy generation, the battery storage, and any loads that might be part of the microgrid. This secondary level would include black start capability. The tertiary level is associated with remote connection to the grid, how the microgrid is interacting with the larger grid. It would include things like price signal following, battery operation, load forecasting, demand response based on current grid loading. So the secondary and tertiary levels of control must interact cooperatively to determine how the microgrid competes in wholesale energy markets or ancillary services like frequency control or.
What are some of the market trends that are driving growth in microgrids?
There's a combination of drivers in the microgrid market. One of the most fundamental things is to look at the history of the very first microgrids. What were they? They were diesel generators and UPS, or uninterruptible power supply systems. These were systems that needed to provide power at high reliability or for places where the grid couldn't reach. Our entire economic system is dependent increasingly on reliability. Our internet, our servers, our cell phones must be highly reliable, and the grid must be able to provide that kind of power. And where the grid can't do that, microgrids fill in the gap. So amongst the drivers, though, are government regulations. The FERC Order 841-845 was a very huge order in terms of encouraging the ISOs and RTOs to write regulations that suddenly now allow grid-scale batteries to compete in the wholesale energy market and also in ancillary services. A grid-scale battery is an instant microgrid. The NERC regulations insist that utilities must meet certain reliability standards. Of course, another driver is always the various tariffs and government incentives and subsidies, I guess you could call them, for various kinds of energy-related resources. And that goes across the spectrum from gas, oil, nuclear, as well as wind, solar, bio. So the other big impact that has happened is the development of the lithium battery has essentially allowed a grid-scale battery in a box down at a price level that can at least compete with short-term storage. PJM proved this with frequency control with lithium batteries. So those are all drivers that encourage microgrids. As far as inhibitors, again, it's similar. Regulations can both drive and inhibit. If the grid is reliable, clean, low cost, there's very little incentive to make a microgrid. If the price of grid-scale batteries is very high, that may limit at least the size of the microgrid, the amount of storage a microgrid would have. There's still plenty of other technical constraints as well in terms of grid operators, regulations, the evolution of equipment, and the transmission and distribution infrastructure in some cases is too weak to support certain microgrids. So there's certainly a very dynamic activity in terms of drivers in the microgrid automation market. Another thing worth mentioning is the relationship between renewable generation, especially solar, and grid-scale batteries. This is a very important factor. Batteries help renewable operators increase self-consumption and reduce curtailment. This will become increasingly important as the percentage of renewables on the grid increases. With massive investments in mining and battery factories, the problem of lithium battery availability is starting to ease. The shortage we've seen will eventually be satisfied. It should be noted that 90+% of batteries are slated for EV production, and the utilities are already planning how to integrate electric vehicles for load control. Vehicle to grid, V2G, will certainly emerge as an EV option in the future, although no US vehicle manufacturers offer this option today. Another factor that will become important is second life batteries. End of life battery for an EV is much shorter than for stationary storage, so used EV batteries could be repurposed for solar storage, and EV RECs will also provide a big source of storage. Let's consider a couple of examples of the importance of reliability. Suppose you lived in Puerto Rico after Hurricane Maria, where your electric grid is completely destroyed, with no chance of getting electricity from the local power grid for 6 months or maybe even a year or possibly longer. You then get very motivated to get a diesel generator and then very quickly get motivated to add solar panels and a grid battery. The rebuilding of the Puerto Rican electric grid is also an interesting case. Some of the proposals have 8 mini grids, divide the entire island up into 8 different sectors, all interacting together as one system. So the future grid architecture seems like it might be different when you have a chance to start from scratch. And a second example is consider Pacific Gas and Electric outages. 2 million people with their power shut off for, in some cases, a week at a time. Well, if you're running a business, a restaurant, a gas station, and you have no electric power, you're going to find a way to make that electric power. And it's also a big motivator for PG&E to redesign their grid so that they don't have to shut down so many people all at once and can more accurately isolate power outages where the highest fire risks occur.
What would you say has been happening recently that impacts the microgrid market?
Grid-scale energy storage is widely recognized as an unsolved problem, at least unsolved for the situation where you need to store electric power for weeks, months, or even a season. For low duration storage, flywheels, lead acid, advanced lead acid, lithium, and a number of other battery chemistries are certainly possible. Pumped hydro was originally developed to help complement the steady load issue of nuclear power plants, which had no place to put power in the middle of the night where there was no load. They pumped water and got that power back for use at peak load times. This chart plots energy storage on the x-axis, energy stored capacity in megawatt hours versus power delivery in megawatts, and you can see that means it is lines of storage duration. And you can also see that there is no options that really are available in the weeks to months to year time frame. There's plenty of options that are available in the frequency control range for 1 second, but a lot of new technologies are developing. There's a lot of new flow batteries. Lithium is the dominant grid scale battery today. I don't think that will stay the case in the long term. Batteries with cheaper materials and probably flow batteries will eventually emerge to overtake lithium.
Makes sense to me. What will drive developments in microgrids in the near future?
Microgrids happen when utilities cannot provide reliable power. Both China and India have made huge progress over the last decade to power virtually all villages in their respective countries. China has been a pioneer in high voltage DC transmission. The Indian grid still needs a lot of work for reliable power. With China, the world leader in lithium battery production and PV panel production, the transition away from coal to solar and wind means strong growth in microgrids. For countries or rural areas without power, the original microgrid was a diesel, propane, or gasoline generator used to provide power on demand. Generator companies like Caterpillar Tractor, Generac, and others have expanded their capability to provide PV and storage as a way to reduce fuel cost. Electric power is now coming to Africa, with many new innovations for DC microgrids, nanogrids, and cooperative connections of households driven by the low cost of solar PV and batteries and the need for cell phone charging, lighting, refrigeration, and future appliances and electric vehicles.
What about over the long term? How do you expect microgrids will evolve?
Many sustainability targets for towns, states, countries, and global accords are setting low or zero carbon goals for 2050. So we're going to consider 2050 as the long term. And these will impact the architecture of, of electric grids and the growth of microgrids. As we have seen, microgrids have a strong relationship to renewable energy and battery storage. The long-term sustainability goal to 2050 is to make electric generation nearly carbon-free, and then with clean electricity to electrify the transportation, building, commercial, and industrial sectors. This is a massive undertaking. This 2018 Lawrence Livermore chart has been produced every year for the U.S. and is not too far from world situation, and it gives a good view to this big picture and the difficulty of the problem. For example, take a look at the contribution of the non-carbon producing generation of solar, nuclear, hydro, wind, and geothermal. It's not very big. And then imagine the generation mix that will be required to decarbonize the overall electric consumption, considering overall energy consumption, not just electricity, while considering the world population is still increasing and developing countries will increase their energy intensity as they upgrade transportation, buildings, and industry more like what we have in the US and Europe. Of course, energy efficiency will help, but overall more energy is required. And the question is where it comes from, and will the future electric grid look more like a cellular network of microgrids? Hydro is nearly maxed out, and biomass for energy competes with farming for food production. But some farms do have innovative bioenergy systems with microgrids, so there is a role definitely for biomass. It's hard to imagine how solar and wind with the needed energy storage could meet this need by 2050, as the required level of expansion is so massive. Geothermal energy is hard to convert to electric power and is not uniformly distributed, so it has a minor role. Nuclear is currently stalled with about 450 plants worldwide, as current reactor designs and fuel cycles have proven problematic, and with a lack of public support as a result of Chernobyl and Fukushima. It would seem new, safer nuclear designs and fuel cycles optimized for energy production would certainly be an option that is feasible. Carbon capture and sequestering may play a role, most likely with natural gas generation, much harder to do with oil or coal. An electric grid with many interconnected microgrids is more likely with non-dispatchable renewables, as they will increasingly need energy storage as they make more of the grid's power. Solar especially can be deployed nearby loads, and it will not be uncommon for households in 2050 to have their own micro or nanogrid with solar PV on the roof and an electric car that can power the house overnight. Should nuclear and carbon sequestering gas power plants provide this future generation, they would tend to be larger, maybe in the rough range of 200 to 1,000 megawatts in size, and thus they're less likely to utilize a microgrid architecture. Grid storage is still a major issue regardless of which way we go. One thing that can be certain is that consumers of electric power will be much more involved with load shifting, as power pricing in most locations will change in near real time at every location in 2050. Such demand response functions would certainly be part of the scope of a micro or nanogrid, but many of these automation functions could stand on their own, using smart home and smart city communications that connect smart meters, smart circuit breakers, smart thermostats, smart appliances, and smart electric vehicles, with many new applications for smartphones, tablets, and computers. The new business models interacting with individual consumers and utilities are being developed to make an interactive electric grid, transactive electric grid, a real possibility. In the time frame of 2050, it's pretty unlikely that we will interconnect all the electric grids worldwide so that when it's sunny on one side of the planet, it can power the dark side. But in any event, there will be an awful lot of changes on the transmission system to bring remote generated power to the population centers, and lots of changes in the distribution and transmission side. Energy storage is certainly a part of any future electric grid. And as non-dispatchable renewable generation will be part of the future grid solution, the need for storing electricity will only grow. Options for energy storage include gravity, batteries, thermal and chemical, and some of these options are more compatible with microgrids than others. So let's take a look at these different options and how they might be involved with microgrids. Large storage systems like pumped hydro or hydro operated for storage can stand alone as a grid asset. But small storage systems near generation and loads can be operated as part of a microgrid. Pumped hydro is the lowest cost, highest capacity storage today, far outpacing any lithium battery technology so far. And pumped hydro can recover about 65% of the consumed energy using reversible Francis turbines. But they are hard to site, take a long time to build, and are not typically part of a microgrid. They're just too big to be a microgrid. Other gravity-based systems like stacking concrete blocks with power recovering crane or pushing loads of earth up a hill or a rail system are in development, but large installations may be a standalone grid asset. However, smaller systems could be part of a microgrid. Lithium batteries are increasingly a part of microgrids with a round-trip efficiency of about 95% and high power capacity. They have proven useful in nano and microgrids. Grid operator PJM proved they are effective for frequency control applications to help stabilize the grid at very high speed. There are many other ancillary service functions that battery-based microgrids can provide. Microgrids that are part of large commercial office buildings or college campuses have very effectively used thermal energy storage for cooling loads. Buildings can make ice, for example, at night with electricity and use that ice to cool the building during peak loads. Molten salts, eutectic mixtures, and other thermal storage media can be used to shift loads by hours or even days in warehouses. Concentrated solar generation can use molten salt to shift the generation till later in the day, more synchronizing with peak load times. And even heat pump manufacturers have added load shifting energy storage as an option. As for chemical energy, outside of normal photosynthesis of biomass, the main candidate for chemical energy storage is hydrogen, although ammonia, methane, and methanol are potential options. Proton exchange membrane or PEM electrolysis and alkaline water electrolysis are two candidates for hydrogen production. And fuel cells can be used to convert hydrogen back into power. Or there have been diesel engines that have been converted to run on hydrogen that could convert hydrogen back to power. Such systems could be part of a microgrid, but so far the high cost and complexity coupled with low round-trip efficiency has limited the market growth.
Thank you for attending this ARC webinar on microgrids. We hope that you found it informative. I would also encourage you to investigate ARC research on microgrids and other electrical grid infrastructure, substations, transmission and distribution SCADA systems, for example. If you have any questions, you can contact me at the email address below.